All right, David Kahn here with another IB question on stellar characteristics and stellar evolution, and the Hertzsprung-Russell diagram. This question about the nature of stars, and we have the Hertzsprung-Russell diagram. On the diagram, there are 4 stars, A, B, C, and D, as well as our Sun. Taking a quick look at the diagram, we see that the x-axis has information on the temperature of the stars, and the y-axis has information on the luminosity of those stars. We notice that this scale is not linear. Instead, it's powers of 10. And we notice this scale is actually going backwards, so the temperatures are dropping. And that's normal for the Hertzsprung-Russell diagram. That shouldn't be too surprising. We're asked to state alternative labelings for the axes. So presumably they mean not changing the numbers, but changing the meaning of the axis. What else changes in the same way as the temperature and the luminosity of these stars? Well, for the x-axis, we know from Wien's law and Stefan Boltzmann's information that the temperature of an object affects the color of the blackbody radiation. And the hotter the object, the higher the frequency of the typical emission. So we could replace this axis with the discussion of color or spectral class, which is a fancy way of saying color. For the y-axis, we have the luminosity at the moment. What else is tied to luminosity? Well, the brightness of the star. Not the apparent brightness necessarily, because that will also depend on how far away we are from the star, but the absolute magnitude will depend only on the luminosity. Okay. Next up, we want to guess which type of star A, B, C, D are. We'll start with A. A is on the main sequence. The main sequence is everything sort of in this stripe, which D is as well. So A and D are both main sequence. C is down here with the white dwarfs. There's not really anything else around there, so the C is pretty clearly a white dwarf. And B is going to be either a red supergiant or a red giant. To tell the difference, we just have to recognize that the supergiants are up higher than the regular giants, higher on the chart. They have higher luminosities than the giants. The giants would be down in this region. So up here at the top of the chart, but off the main sequence, we find the red supergiants. All right. Explain, using information from the HR diagram and without making calculations, how astronomers can deduce that star B is larger than star A. So presumably, star B is larger than star A. Well, the first thing that I notice is that star B has almost the same luminosity as star A. Oh, well, by almost, I mean about 10 times more, but I guess they're similar. So B is more luminous than star A. But at the same time, B is much cooler than star A. And so it's emitting more power, but using lower energy photons. So it must be emitting many, many more photons. And to emit that many more photons, it must have a larger surface area for those photons to come from. So let's see if we can put that in. Star B is both more luminous and lower temperature. So it is emitting, so it must be emitting more photons. Well, we'll put a little statement in the middle there. It's more luminous and lower power, so it is emitting lower energy photons. Basically, redder color photons are lower energy than bluer color photons. Hotter objects are bluer than redder objects. So this cooler star is emitting redder photons, lower energy photons. Therefore, it must be emitting more photons. To emit more photons, more photons than the sun. To emit more photons, it's not the sun, sorry, star A. To emit more photons, it must have more surface area. Hence larger. Hence it is larger. All right. Using the following data and the information from the HR diagram, show that star B is at a distance of about 700 parsecs from Earth. This is a tough question. They gave us a lot of information to try and put together here. We know the apparent brightness of the sun, the apparent brightness of star B, the distance from the sun to the Earth, and 1 parsec in atomic units. Astronomical units. Okay, so let's go to what we know. We know apparent brightness is equal to the luminosity divided by 4 pi times the distance to the Earth squared. Rearranging this to solve for luminosity, we can say that luminosity is equal to apparent brightness times 4 pi times the distance to the star squared. But the issue is that we don't know the luminosity. We only know the luminosity relative to the luminosity of the sun. So the sun has a luminosity of 1 sun worth of luminosity. Star B has a luminosity of 10 to the 6th, 1,000,000 suns worth of luminosity. So we can't solve for the luminosity. We can only solve for the ratio of the luminosity of star B to the luminosity of the sun. We can only solve for one in terms of the other. So we can say the luminosity of star B is related to the apparent brightness of star B and the distance of star B to the Earth. And we'll divide that by the luminosity of the sun, which is the apparent brightness of the sun times 4 pi times the distance to the sun squared. 4 pi cancels out, and we're left with an expression that we can attempt to solve for what we're looking for, which is the distance to the Earth from star B. That's this term here, without the square. So that term is equal to LB on LS times BS multiplied by ds squared. All of that divided by b, and then take the square root of the whole thing. Yikes. But it turns out that we know all of this. 3 out of 5 are given in the table. It's the luminosities that we don't know, but we do know that the ratio of the luminosity of star B to the luminosity of the sun is 10 to the 6th to 1. That's 10 to the 6th. 10 to the 6th is LB divided by LS. At the same time, we know the apparent brightness of the sun, 1.4 times 10 to the 3rd. We know the distance from the sun to the Earth, that's 1 AU. And we know the apparent brightness of star B, 7 times 10 to the negative 8. We want the square root of all of that. And so finally we get the distance to star B as 1.4 times 10 to the 8th astronomical units. We wanted to show that it's about 700 parsecs, not 700 astronomical units, so we can simply divide by the relationship between astronomical units and parsecs. We'll divide by 2.1 times 10 to the 5th astronomical units per parsec. And that gives us 670 parsecs, which is about 700. Whew. Finally, we need to explain why the distance to star B from Earth cannot be measured by the method of stellar parallax. The problem is this right here. That's quite far. That is a few thousand light years away. Star B, Star B is so far away that the parallax angle can't be measured accurately. Well, that's really all it is. It's so far away that the parallax angle is so tiny that we just really can't take a measurement of it.